Before we go ahead and start learning geodesic equation part 2, here is a quick recap on what I have covered in the last video, which is quite important. Now first we have covered the origin and the meaning of the word geodesic. So just kind of an etymological meaning of geodesic, where it came from, what actually it means. Then we have covered that there is a wrong notion that geodesic is related only to relativity. However, it is not, and I have showed two examples of two famous books that it is basically a very important concept which is taught in differential geometry, and it is then used in general theory of relativity. Third, I have explained in the last video that what is the meaning of the geodesic equation, the general geodesic equation, what are the components, what is the meaning, and so on. Also have mentioned that the need for the geodesic equation, or rather the usage of Christoffel symbols, comes when the basis vectors change in a manifold. If you go to my last video, you will see that I have shown that basis vectors do not change in a Cartesian coordinate, but in a curved manifold, like in case of spherical manifolds and so on, it actually changes. I have shown also what are Christoffel symbols, a kind of a visual and intuitive meaning of that, and then we have looked at deciphering those Christoffel symbols, what is the meaning of the dot product, the basic vectors, the derivatives, and so on. So the first video essentially covered the overall meaning of the geodesic equation as taught in differential geometry, Christoffel symbols, and the need for using those Christoffel symbols. In today's video, we will start with the geodesic equation as used in general theory of relativity. However, I will keep a comparison with the general geodesic equation so that the learning is much easier and much more profound. So here are the two equations. The first one is the general geodesic equation, and the second part is what is called the geodesic equation used in general relativity. Now first I would like to highlight that the x raised to the power p, the generic term, is now used as x raised to the power mu. And as the Greek indices go from u, then nu, then rho, and so on, they are actually the space-time coordinates, 0 mentioning the time or the temporal coordinates, and 1, 2, 3 are the spatial coordinates. So the p is now much more generalized as mu, which are used as coordinates over space and time. Now we see that there is a s square at the denominator, which is being replaced by the Greek letter tau, or tau squared. And here you can see that there are several d tau, d tau. I will come to that part in details, but let us understand this tau is replacing the s, which is, we will see, is the affine parameter for the proper time, the natural clock that is carried by the particle. I will show you in visual what do I mean by natural clock when I come to the concept of worldline. So right at this moment we can understand that xp is replaced by x mu, which are the coordinates over space time. S, the affine parameter, is replaced by tau, which is basically the proper time. Now we come to the most important part, the gamma followed by a p on the top and ij at the bottom, and this is nothing which is called the Christoffel symbols, and they, from this Christoffel symbol in the general geodesic equation, comes from coordinate systems. However, this geodesic equation, which I am zooming right now, is basically coming from the metric tensor. So here is the difference. So the general geodesic equation Christoffel symbols are basically pure definition of geometry. The Christoffel symbol in the GR is basically derived from the metric tensor G mu nu. However, I am not showing the derivation to avoid the complex mathematical calculation. Then we have got the x nu, x rho, etc., which I will come, which is the differential part of the coordinates. Now, most importantly, why do we set the equation to 0? I will explain it, but just an overview. It means that the particle is not being carried by any force. That means there is no external force which is happening. It is just following the natural path. So here is a diagram that in flat space, if you draw a straight line, it is moving at a constant acceleration, constant speed, so your acceleration is 0. And in curved space, the same A and B, which is that red line, which is a sphere, it shows that it follows a natural path. That means there is no external force which is happening on it, and that actually justifies that why the equation is set to 0. Now, having said that, I would like to explain the other components of the generic version and the GR version. Now, in the generic version, here you can see that it actually tells you the shortest or the straightest path, and d square xp by ds square, it actually xp means the pth coordinate function. That means it can be p, it can be s, but it is a coordinate function. So here I draw a kind of a curve, and here I take s as what I have discussed earlier. You can go and understand what is a affine parameter. If I click here, the S path will move from here to here. So this is a nice animation which actually shows that S is the affine parameter, and it is just like a ruler. You are sliding along the curve and it is measuring that curve, nothing else. So here the interpretation is that there is no physics, there is no space-time. It is a rule for straight line or curved spaces. Now let us look at this, which is the general geodesic equation. Here you can see the tau, which is replaced by s. So the s, which is acting as an affine parameter like a ruler, now it is acting as a proper time, because time is also moving, the parameter is also moving. So it is the proper time experienced by the moving particle. So what it says, again I am justifying why it is set to 0, that describes the motion of freely falling particle, that means it is not experiencing any acceleration or any gravity. Gravity is already built into the curvature through the Christoffel terms. So here you can see this d square x mu upon d tau square is basically the x mu, which is representing ct, x, y and z. And those who are aware about special theory of relativity, you know these are nothing but what? These are space-time coordinates. So from here we can definitely draw a kind of a comparison between the aspect, the general geodesic equation, the relativistic equation. So the parameter, which is s, which is often used as an arc length, is now used what? As a proper time. That means the physical clock, the clock which the particle is carrying. If we take off space, then remember that general geodesic equation happens in any curved manifold, but the relativistic part takes care on a 4-dimensional space-time, where 1 is the time dimension and 3 are the spatial dimensions. If I talk of the meaning, then this is pure geometry. Although the meaning is the same, remember, but it is in general geodesic equation is pure geometry. There is no physics involved, so it is shortest path on a surface. If I talk of the relativistic part, it is a free falling trajectory under gravity. I will show you more elaborately what does 0 actually means. And the nature of curvature is little bit abstract in case of a mathematical. Obviously in mathematics we deal with abstract things, and this is the real space-time curvature, which is caused by the, you know, the stress energy momentum tensor T mu nu, which is the mass energy part. So from here what we can say definitely is that d square, this component, is geometric pure straightness. Right, and in case of this part, this is in pure physics. In physics, it is a free fall. So we can conclude that in pure geometry, a measure s measures how far you move, but in relativity, tau, which is replaced by s, s is replaced by tau, measures how much you experience while moving. So remember, both describes geodesics, but one belongs to the surface and other belongs to the space-time itself. Now once we revisit these two equations, there is something which you might think to be familiar to that of an acceleration, second derivative of time with respect to this. So my question automatically would be that, does this denote a kind of an acceleration? Because if you go to Newton's Newtonian mechanics, the basic equation of acceleration would be something like this. It will have a derivative, it will have a second derivative of time. But this is a big question, that does this denote acceleration? Now in order to answer this question, first of all I would like to tell you that in a general geodesic equation it looks like an acceleration, but it is not a physical acceleration. So if you go to Newtonian mechanics, d square x by dt square is obviously an acceleration, but it is not here. It is simply the second derivative of position with respect to the path length, which is the ds square, and it shows how the direction of the tangent changes the path. I will tell you what do I mean by tangent changes to path, but first of all you need to understand it is simply the second derivative of position with respect to the path length. That is how the direction of the tangent change along the path, and it is purely geometric in nature. This is important. It is purely geometric curvature, not a force induced acceleration. Just the way we look at Newtonian mechanics, it is not a force induced acceleration. So it is just a change of direction along the curve. Now if I take two cases, for example, if I take case 1 where I am taking a flat space or a Euclidean space, then here the coordinates grid is straight. Obviously you can see there is no curvature correction. So obviously the geodesic equation or the Christoffel symbols don't need any corrections, so it will reduce to 0. So if this second derivative were not 0, it would directly mean that this part object is accelerating in the physical sense. That means there is a change in velocity. So first is that if the coordinate when it is straight, the Christoffel symbols reduce to 0. If it was not 0, it would directly mean that the object is accelerating. This is in case of a flat space. Now, so from here what we can say is that yes, in flat space it does represent acceleration. But now we deal with a curved space like a sphere. So in case of a curved space, what you can see, the coordinate grid itself is curved, isn't it? This grid looks curved, meaning even a straight motion looks curved when it is described in those coordinates. So obviously d square xp by dx square will be not equal to 0. That is true. So what does it mean? Now this one not equal to 0 does not mean physical acceleration. It just means that the path appears to bend across the coordinates. Now if I go back earlier, here I told you that if it is not 0, then it will be acceleration. And if it is 0, then there is the Christoffel symbol don't need any correction. But here what I am telling is that it does not necessarily be any physical acceleration. It just means that the path appears to bend because the coordinates are bending. And from here what we can see is this kind of a curve. Here the Christoffel symbols accounts what? The Christoffel symbols basically accounts for the curvature. So when you add it in the true acceleration, I would say the covariant acceleration, obviously it becomes 0 because the motion is actually free and forceless. So in flat space time where the Christoffel symbol equal to 0, the same term does become true acceleration because there is no curvature. So in short, what we can tell is that this particular, the first element of the geodesic equation in flat space time, it looks like acceleration, and in curved space time it looks like 1, although it is really the geometry twisting beneath you or the geometry which is happening. So again, let us revisit this concept. It is only acceleration in case of a flat space-time, but in case of a curved space-time, it looks like an acceleration, but it is not, because there are Christoffel symbols. That means it is accounting for curvature, and then it is not equal to 0. And also, as I told you, that the derivatives are not 0, and the basis vectors change. These are also intrinsic part. So you can go to my first video and watch it, that why I am telling that derivative is not 0 and the basis of the vectors change in case of a curved manifold. Now we will come to the next part where I am trying to explain you what is the meaning of this S parameter. Now this S parameter, as you can see, has been replaced by the tau parameter, which is the proper time in case of a relativistic equation. So S is nothing but it is a kind of a parameter in curve. So in relativity, actually we represent a motion of a particle not just in space but in space-time, that is both in space and time. The question, as I asked you before, is that what should S represent physically? So as I have already told you, it describes the particle moving through space-time. So we want the parameter to represent something real. So the time that the particle itself experiences as it moves, this is represented by a proper time, which is tau. And you have already recognized by the right hand side of the screen which you are watching now, it is basically the Minkowski or the space-time diagram or the light cone, whatever the way you want to tell. So a particle's path through space-time is called a worldline. So if a particle is at rest, a worldline is straight or vertical. but time passes, but its spatial position does not change. The light cone actually shows the limit of which how light can travel. You know already that 45-degree lines where c is equal to 1 represent light rays, and anything inside the cone is causally connected. A particle can move there and appear. Anything outside is unreachable, because hypothetically it would require a faster than light travel, and we know special relativity restricts anything moving faster than the light. So this is what the S parameter is, and in relativity we want, because we want the parameter to represent something real, so the time that the particle itself experiences is called as tau. Now if I want to take the same this space-time diagram, on the right hand side you can see this animation which shows a particle's path which is through a space-time. It is called the world line. Now if I want to connect it mathematically, how will I do it? Very simple. We are connecting the visual idea, s square is equal to c square t square minus x square, which is coming from special relativity, and s is nothing, or s square is nothing but the space time itself. I would interval, that is the like distances in space time. And here you can see if it moves, the world line tilts more. That means more faster the particle. Here you see now the particle is moving. Now here it is, the particle is moving faster, so the world line is actually tilting. So here this actually gives you a nice visual understanding of how a world line actually behaves. Now if I take an analogy and try to make you understand to a path, then I would say that the world line is the path of the particle through space-time. That means somehow you are walking through the road, so that is called the world line. That means the particle, how is it moving? So the space-time interval here plays a very important role. The role is that the distance the particle travels is something just like the Pythagoras' theorem, ds equal to dx squared plus dy squared. And in relativity, because we have 4 dimension, we extend this relation to this. So this is actually the Minkowski metric that is analogous to the space-time diagram of the Pythagorean theorem, with a minus sign for spatial dimension. And if you really want why this minus sign and plus sign happens and what are the signatures for all those, I have got a video on my course on General Relativity where I have highlighted explaining the minus sign, the hyperbolic, the Poincare disk, everything is there. You can go ahead and understand. So this part actually shows the geodesic equation in general relativity, what is S, what is tau, and the concept of world line, and how do we connect very easily from the Pythagorean rule to the relativistic space-time interval. Now here is another important thing which you should notice, that you see that the general geodesic equation, which has got S as an affine parameter technically, or you can just tell it is an arc length, now it is being replaced by what is called tau. Now how does it happen? Is it just a kind of a mathematical trick or something like that? Here you can see I have highlighted the blue arrows denoting the S, and these red arrows or the maroon arrows are denoting nothing but the tau. Now here what I am trying to explain, that replacing S with tau in the general geodesic equation gives you the relativistic equation. Obviously that is the thing, but question is that is this just a mathematical solution substitution, or it has got a very deep physical meaning? Now this is something which I would like to explain, and it carries a profound importance in differential geometry and general relativity. Remember, we have talked earlier that S is just the parameter. That means you are walking from your home to the nearby shop. It is just the distance along a curve, which is called the arc length on a surface. So this is the arc length, and if I animate, it will move from here to here. Simple. Now in general, this x mu within braces S, it actually tells you the coordinates of a point. So this equation actually says that the curve's tangent does not change direction if it is a geodesic. That's it. So it is basically nothing, but it is a purely mathematical statement. Again, we are going a transition from mathematics to physics, so it is purely a mathematical statement. Now when we come to relativity, our curve is not living on a tabletop or anything, it is living in space-time. So now we are not talking about a surface anymore, we are talking about a world line traced by the particle. The left hand side animation actually helps you to visualize what is a world line. So as I have told you, when a particle moves through space-time in a world line, it actually, its path traces both space and time. So particle's motion is denoted by this. and it traces a world line. So to describe where it is, I mean to say the location that the path we need a ruler or clock to measure the progress. So for that, as I told you, this space and time is not different. Now it is intertwined in what is called space-time diagram. So here you can see this one, this part which came, this is the tau. So we use a proper time, the time measured by the particle's own clock. So if this round circle is basically the particle, I have put up a clock. So this is the particle's own clock, and this is the proper time, and it is denoted by the Greek letter tau. Now this tau is the same for all observer and gives a kind of a natural universal way to mark the progress along the world line. So why we are doing this tau and replacing this s? Because it is invariant and it is the same for all observers, and therefore perfectly suited to describe motion in relativity, because we know the basic foundation of relativity is what? Is that the laws of physics should be invariant irrespective of whatever frame of references that we are making, or that we are seeing. So if you imagine a tiny step along the particle's path d, then d tau is nothing but it measures how much the particle itself experiences, that how much particle itself is actually moving. So this is actually what it tells. Now when we substitute, now let us do the substitution. So that is the reason I would say we parameterize this as x mu within braces t, not s, because now we are not dealing with arc length, we are actually measuring what? The particle's actual time, because the particle is traveling in world line. Now since the particle's path is now being described by its own proper time, the equation becomes simply this. So all the s are simply substituted by what is called the tau, which is called the proper time. So this is, remember, this is not just a symbol of substitution, it is replacing an arbitrary mathematical parameter s with a physical invariant tau, because it describes the real time for the particle. So this is the geodesic equation in general relativity. S being the abstract distance now is replaced by tau, the proper time, and you can see all the taus happening over there. And here we can see a free particle moving along the path makes its proper time stationary. And that is what is called the annus mirabilis, which Einstein found when he was sitting at his office at Bern, Switzerland, that if the floor is collapsing and he is falling down, that is called the principle of free fall, or the equivalence principle, that you really feel weightless. And from there Einstein actually found out that there is nothing called gravity locally. So that is the principle of free fall. The particle experiences no force. So here we justify, and I try to show you, explain the s arc length being replaced by tau. What is tau? The world length, etc. We come to the final part of our video, where I would like to explain a very fundamental concept, that why this equation is being set to 0. Now if I take the generic again the differential geometry equation, then this 0 is basically telling that the tangent vector does not change direction intrinsically. I will tell you what I mean, because this is something very important. Now because the geodesic is defined as the path where the tangent vector does not change direction intrinsically, in flat space no change of direction means a straight line or zero acceleration. Here you can see on a book I have drawn a diagram, the arrow, there is no change in the tangent. Because a geodesic is defined as a path where the tangent vector does not change intrinsically on the flat surface, it is the straight. Now here I would like to give you a quick note, a kind of an understanding. Now this concept of tangent vector, what we learn in school level geometry, we say what a tangent line is just touches, or a line that just kisses a curve at one point without cutting through it. This is the school level geometric idea of what is called the tangent. Now when we talk of differential geometry, our context, I mean to say geodesic curvature, a tangent is always not a full line but a direction vector at a point on the curve. This is important. The tangent vector in case of differential geometry tells you which way the curve is heading at that point. And it is defined by this, which is the derivative of the position vector with respect to a parameter, say s or tau, whatever. So this is very important. So the tangent vector in differential geometry tells you which way the curve is heading at that point, whereas in a school level geometry it is just something which touches the line. This one is defined by the derivative of the position vector with respect to any parameter s or tau, doesn't matter. So the tangent vector is not a line that touches but a direction, the instantaneous velocity of the curve at that point. This is the tangent vector concept in case of differential geometry. So yes, here also we can say the tangent line still kisses the curve at a single point, but more importantly, its direction stays constant as you move along a geodesic, which is called a straight line. Now let us come to the next concept. Now when we set it to 0, as I told you, that it actually technically means that the curve's tangent vector is being parallelly transported along a surface as straight as possible. Now this requires an attention. What do I mean by parallelly transporting? Now if I take a Euclidean surface and if I take a kind of any triangle, isosceles or equilateral triangle, what I am trying to do now is that I am trying to take this blue vector and loop around this Platonic surface, we call it Platonic surface or the Euclidean surface, in this way. I will move starting from now and I will keep the vector as straight as possible. So here I move, and I go and I go and I go, and when I come back, this red vector you will see exactly overlaps with the blue vector. So that means the vectors are the same. That also means that if you start and end at some point, the move vector perfectly overlaps with the original one, which signifies that the surface is placed flat, or I would say the manifold technically is flat and it has got no curvature. So here is the animation. It shows that you are looping around. You're trying to transport the vector along this Platonic surface and you're coming, which is overlapping with the original vector. Now if I take a kind of a sphere, which is obviously a curved surface, and here I am standing at this purple point, I take a vector which is v and I start moving from north pole in this direction. I move here, I move here, I move here. So this is the arrow which is showing. I further move here, I come down to the equator, then to the poles, and then here, and then when I end again over here, this direction, what I k is a v prime, which shows that there is a gap. So the yellow vector, which is the v1 which I originally started, is not overlapping and there is a gap between the v and the v prime. This mismatch you can tell. So again it is looping around, right? Technically we should say it is looping around. So this mismatch is the fingerprint of curvature. That means that keeping vector the same still causes it to change the direction globally, and that tells that the surface of space-time itself is curved. So this is what is called of a parallel transport, and the Christoffel symbols and setting to 0 actually means it is being parallelly transported. In the first Euclidean case we parallelly transported, but we overlapped the vector signifying curvature is 0, and here we are parallelly transporting and we are seeing a gap, which is called why the space-time is being curved. So from here what we can see is this 0 actually means that the acceleration is entirely due to the curvature of space-time. There is no extra force pushing around which is happening. So this part actually shows that the free particle moves with a constant forward velocity. I hope you understand forward velocity along a straight line trajectory in Minkowski space. And a free falling particle in GR actually experiences no force. Obviously not even gravity, because here gravity is not a force and it is purely a geometry. That's it. So from here what we can finally draw a diagram is this one, and if I got a red dot which is over there, and if I try to move along this trajectory, this black one, I'm trying to move from here to here, you see that I will just take an animation. Slowly it will move from here to here. Slowly it will move from here to here. So moving from here to here, if I take a person who is looking from outside, that person might see that there is a force. Okay, because it seems like somebody is pushing and the particle is moving. But it is not a force, it is arising naturally from the curvature of space-time. And hence, however, this acceleration is caused by a force in a traditional Newtonian sense, obviously. So here we finally conclude there is no force which is pushing it, but it is purely following the geodesic, or the particle which is following the manifold, the path. It is following the straightest possible path, but because the manifold is curved, hence it shows that there is a curvature, and the person who is watching from outside seems that there is a force or some external hand or force which is making the particle to move. So the acceleration is nothing but a consequence of the geometry. It is important. It is not an external force, it is a consequence. So curved space-time, that is a sphere or anything, actually dominates. It dictates and tells how these paths appear as accelerated motion to observers. That means a person who is watching is not watching the right thing. It is basically the accelerated motion to observer which seems to appear because of the curvature. So here is a quick time to summarize what we learned today. We learned what is the definition of a geodesic, what is general mathematical generic equation, Christoffel symbols we have seen in this and the other video, how proper time is being, the arc length and the proper time, how they are replaced each other, relativistic geodesic equation, why the equation is being set to 0. This is important, principal equivalence, and there is no force, and the flat versus curved visualization in case of a parallel transport. So that's all for today's video. Thank you for watching Physics for Students, and if you have liked this video, please do not forget to subscribe and click on the bell icon to get all the notification from Physics for Students. You can follow me on my social media handles, especially in Thread, where I'm putting up a lot of interesting stuffs, not always related to pure mathematics and science, and you can write to me at this email ID, which I try to respond as early as possible. I know I have been a little bit late in posting videos because a lot of traveling and my other commitments in terms of correcting my papers, helping the mentoring PhD students, and a lot of other things coming up in terms of science development and research. But I promise I will be regular and posting more videos on this channel. Thank you for watching. See you soon, and may the good Lord be with you.